Let us now spend some time learning about numerical integration. The ideas are fairly simple and are based on the interpolating polynomial expressions we developed earlier. Now, this is a schematic that will be used to develop the formulae for numerical integration. Basically, you have the independent variable x that is plotted on the horizontal axis. The dependent variable y, which you can also denote as f of x, is plotted on the vertical axis. And we have access to data, and the data are tabulated like this. The first data point is x0, f0. So this is the value of x0, and x0 also happens to be equal to the numerical value a. So x is a symbol, x0 is a number, which we can also call it as a. And the corresponding value of f is f0. Then the second data point is x1 and its corresponding f value, which is f1. So this is the value, x is equal to x1, and the corresponding value of f is f1. The next data point is x2 and the corresponding f value is f2. So this is x2, x is equal to x2 is located here, and the corresponding value of f is this. And so on. When you go to the ith point, the x value is xi, and the corresponding value of f is fi. That's what is indicated here. And the last data point is xn, and its corresponding f value is fn. So this is xn, and this value is fn. Xn is also denoted as b, like x0 was denoted as a. So we are actually looking for this integral going from a to b f of x dx. So we are trying to find out that integral. An integral is nothing but the area under the curve. What we have here is we may not have access to the true f. If we had access to the true f and it was an easy expression like a polynomial or something that we are able to integrate by hand, we can do that already, right? We have already learned the topic of definite integrals in high school or in year 1 of an undergraduate curriculum. But we can do that by hand or by using computer algebra only if the expression f of x is known and it is easy. However, if we have only data like this, how do we estimate the value of this integral? Of course, we know by now we can convert this data into a suitable polynomial, and you can integrate that polynomial. So what we are going to do, as you might expect, is we are going to construct, using the data, we are going to construct interpolating polynomials of the order that we like, and then we will integrate those polynomials to get the value of this integral. Of course, since you are replacing f of x by an interpolating polynomial of a certain order, you will have some errors. You will not be able to estimate the true value of this integral. Therefore, the way to acknowledge it is to define the quantity of error that would be expected with the approximating polynomials that we are going to use. Now, in other cases, we may have f of x given to us, but the expression can be very complicated. So sometimes we can have very complicated f of x, so that we are not able to integrate it by hand, or even computer algebra that's possible with the symbolic computing toolbox in MATLAB, for example, that is not able to calculate the value for us. So if integration is difficult, even for computer algebra, then what we do is we use this complex function, we evaluate the complex function at x0, record the value of the complex function, which is f0. We now set x is equal to x1 and then record the corresponding value of f as f1, and we go on until, let's say, we have xn and the corresponding value of the very complicated f of x as fn. So we have created data from a complex f of x, and we are now in this situation. So once you have data, this tabulated data, you can use a suitable polynomial, an interpolating polynomial of a certain order, and then you can evaluate this integral. There are many ways of approaching this problem. For example, I can take neighboring data points. For example, x0 and x1. These are neighboring points, and the corresponding values of f is f0 and f1. So now what I can do is I can assume the relationship to be linear. That means I'm going to connect f0 and f1 by a straight line. So I'm assuming, if you like, a linear interpolating polynomial. The object that is shaded in blue becomes a trapezoid, and the area of the trapezoid is half into sum of parallel sides multiplied by the width of the trapezium. That means the distance between the parallel sides. So width of trapezium. So this is the area of a trapezium. If you apply that to the blue trapezium, half into sum of parallel sides, that means this and this are parallel sides. As you can see, both are verticals drawn from the horizontal axis to f0 and f1 respectively. So it's going to be half f0 plus f1 times, what is the width of the trapezium? The width of the trapezium is x1, which is this value, minus x0, which is this value. So the width of the trapezium is x1 minus x0. There you have the area of the trapezium, which is approximate of the integral f of x dx from x0 to x1. We do not know what the true function is. We do not know what f of x is, but we have only these two data points taken at x is equal to x0 and x is equal to x1. So we use that information and we assume a linear relationship. We assume that f of x is linear within at least this range, and therefore we are able to write this expression. Now assume that the x sample points are equispaced. That means this gap between x0 and x1 is h, the step size. This gap between x2 and x1 is h, and so on. So they are equally spaced points. So if you make that assumption, I can write this blue trapezium to be having area half f0 plus f1 multiplied by h. Now, what would be the area of this trapezium that I am now shading with red lines? So that second trapezium is going to be half f1 plus f2 times h. The third trapezium that I'm now trying to do something with, this third trapezium will be half f2 plus f3 times h. The same formula repeats. So this height is f3. So if you add this thing, you can get the area of the three trapeziums as half f0 plus f1 h plus half f1 plus f2 h plus half f2 plus f3h. I'm just taking the three trapeziums that I've just highlighted there in some way. So this, if you take it all together, we see h by 2 appearing common. So I'm going to say h by 2, f0. And then we have f1 here and f1 here adding. So we'll have 2f1 plus f2 is here and f2 is also here. So we're going to get 2f2 plus f3. So this is the area of the trapezium. Interestingly, the f value at the boundaries, right? The left boundary is f0. If you consider the three trapeziums together, the right boundary is f3. So those come in with a weight of 1 and 1 each. The internal points, which are characterized by f1 and f2, have weights of 2 each. So all you have to do is, once you're given a table, and if the x values are equispaced, first find out h. Then apply this formula. Take this value, take this value, take this value, and let's say the f3 value. Take all those things together and give a weight of 1 for this, a weight of 1 for this, and a weight of 2 for this. And we have the area till the three trapeziums. So if you're going all the way from x0 to xn, you can see that this will generalize to area under the curve. That means the entire integral here from x0 to xn, or from a to b. That's going to be h by 2 f0 plus 2 f1 plus 2 f2 plus all the way till 2 fn minus 1 plus fn. Because the last point will appear in only one trapezium. The left point, the first point, will appear only in one trapezium. So f0 and fn will appear to have a weight of only 1 each. Whereas something like f1 is part of the first trapezium as well as part of the second trapezium. So that will count twice. So all the internal points will count with a value of 2. The extreme points, both of them F0 and Fn, will have a weight of 1. So that will be the area under the curve using this trapezoid idea. Not surprisingly, this is what is called trapezoidal rule. And in MATLAB, the trapz command enforces this. So this is how you can find the numerical value of integrals using some very simple ideas. Of course, you know, we have to do it formally and rigorously. That's one thing. The second thing is we will have to go beyond linear interpolating polynomials. We want to go for second order interpolating polynomials, third order interpolating polynomials, etc. because functions are often complex. They are not linear, even piecewise. All right. So the idea is we will look at higher order interpolating polynomials and derive suitable expressions. And that is what leads to a variety of formulae that are called, for example, Simpson's one-third rule or Newton-Cotes formula or other things. So we will get to that. I will stop this video here and we'll catch up in succeeding videos. Thank you for your time.